Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. The next step I'm going to take on a little mini lathe project is to cut the dovetails on the cross slide and all the cross slide dovetail features. Now there's a couple of different ways you can measure dovetails, and I'm going to show you two ways that I know of. One of them is it just seems so obvious, it's not even funny. And when you see the math, you see the way it falls out, you're going to it's almost too good to be true. So I'm going to show you the first way, the conventional way, with pins. Both ways are with pins, but pins of different sizes. So that being said, let's take a look at the feature, the way the feature is going to be cut on that little project. I am not a big fan of over-constraining a dovetail. I don't need it to hit on the bottom, on the 60 degree, and on the top. 2 of the 3 are fine. You don't need all 3. You just don't. Chances are, you grab a 6-inch scale out of your apron, you can slide it underneath the cross slide because it doesn't touch. Touches on the sides, touches on the bottom. That's what we're going to focus on here. Therefore, the bottom inner corner is the gauge point. That's the point that I want. This can be as deep as you want it to be, but this is the corner that has to make as the thing goes together. My feature is going to be 130 deep. 60 degree dovetail. Now looking at this particular graphic, you're only looking at one side of the female cut. This is the part of the tool post that slides back and forth, compound. 2 pins, 1 on either side, gauge block in the center, that's how you measure it. You do all your math, you come up with the point-to-point dimension, and all is well. How do you find it? Well, let's start doing some geometry here. Unfortunately, dovetails, you're going to have to do some trig, you're going to have to do some geometry, but a 30 degree or 60 degree dovetail, in my opinion, is one of the easier ones. So let's look at the pin. Where are the triangles here? Naturally, there's one right here. 130, 60 degree. Let's put that down here. Maybe you'll be able to see it. 130 base. $60 degree up top. Right there. Triangle A. Let's call it. And that's just so you can come back and freeze frame and stare at it and scratch your head and go, I don't know what he said. Next, geometric construction rule. I'm going to use a nice straight edge to do this. I'm going to draw a perpendicular line from the top, and I'm going to draw a perpendicular line from the side. Because as far as construction goes in geometry, the tangent point of any circle coming up against the corner is a right angle. And we're going to talk right there. Since that's a right angle and that's a right angle, and this side equals that side, because these are the radius. 2 sides the same, bisected angle. This is a 30 degree. This is also a 30 degree. These triangles are the same. It's right there. Radius of the pin. Let's not even consider the radius of the pin yet. It will come into play. Looking at this triangle here, if you were to flip this line parallel over to here, you'd have exactly the same triangle forming a large rectangle. So this distance right here will be translated to up here. Okay, can you see it? Slide it over. These 2 numbers right here, 1 inch, 154.7 and 0.86603, are the 2 most important numbers if you're going to be working with hexes, with 30, 60, 90 triangles. Right there. Lock them in your memory banks, write them on your hand, stick them in your toolbox, whatever. Right there. I am not going to use trig tables because I have standards. I am going to use a calculator to proceed. So Let's see how fast all these numbers are going to fall out of this. Let's call this, just for sake of being smaller than the depth of the dovetail, the pin diameter, I don't know, pick it, 100 thousandths? Let's call it 120, just so it's not a bunch of zeros. Diameter, 120, which makes R 60. All right, 30 degrees on any 30, 60, 90 triangle, which is exactly what you have here. The hypotenuse is twice as long as the smaller leg. So this leg right here, the long one, is 120. Right there. 120. The base leg is 120 times 0.86603. Let's see how that works out. Let's call it 104. It's actually 1039 for everybody that's going to be splitting hairs, but close enough. 1039. Call it 104. All right. Super important. You now have 104 right there. Now what we want to know before we can start using this pin is how far is it from the center to this point, or from the edge tangent of that pin to that point, because really you don't have anything here that's incredibly useful right now. Let's use the same exact math that we just used on this triangle here. As a matter of fact, I'm going to block that out so you can see it. There you go. The 130 multiplied times this one right here will give us the diagonal leg. The 150 150 and a tenth. It's not even worth arguing about. Same thing, and that's this triangle down here. Knowing that, the height, half the hypotenuse, 0.75 right here. Now you got all kinds of good stuff you can use. 104 minus the 0.75, because they're starting from the same place. Where's the difference? Center line's dropping down. There's our dimension we want right there. 0.104 minus 0.075. 29. There is a 29 thousandths difference between the center point of a 120 pin and the corner right there. The radius, 0.60. Gives you your number from here to here, which is the gauge point here. So basically 0.29 times 2, because you've got this gap on both sides of the dovetail, plus 1 diameter, radius times 2. Whatever that stacks up at, subtract that number from your required point to point, and that will be your block size. There's a lot to think about right there, but roll it back, watch it a couple times, it will make a lot of sense. 2 triangles, you find out 2 triangles, you have the difference in the 2 triangles, plus the radius, now you have things you can work with. Gives you your block size. Not all that bad. Now the ideal scenario, and I was just working on this a little while ago, the ideal scenario would be to put a pin in here Now, you don't have to do all this. But what size is that pin? You can just try all day guessing back and forth, right? We want to put a pin in here where the center of that pin is right over that point right there. How do you do it? It's a lot easier than you think. I couldn't believe it when I finally worked it out. And it might be well known, but maybe not. Who knows? Let's check it out. Let's wipe this off of here so you can't see it anymore. Alright, so now you have exactly the same geometry on the outside. 130 deep, 075, 150 leg, 60 degrees, all is well. We want to know what size pin fits in there, that the pin is right on that dot, right there. You are not going to believe how easy this is. Same triangle, triangle A. By knowing it's 075 on the bottom, it's 075 on the top. Bisect the angle, 30 degrees, 30 degrees. Now we're working with the same 30, 60, 90 triangle that we've been working with. Now watch this, this is just going to floor you. When you shoot that corner angle out, it's going to bisect the vertical in one specific spot. Well, guess what? You got 30 degrees on both sides. You've got a common hypotenuse on both sides. Therefore, this leg equals this leg. Right there. Go back to the rule of construction with the geometry, with the tangent point of a round forming its right angle. You now have the center point of your pin right there. It just fell out. So with one triangle, you can find the radius of the ideal pin to put the center over that edge right there. Let's do the math. 075 times 1 inch 154.7. Oh, 86.6. 86.6. The vertical, half the hypotenuse. This is 043.3, and so is this. Now here's the cool part. That's the radius of the pin. So you double that to find the radius of the pin. It's like, oh, wait a minute. I don't even have to double that because it's right here. As soon as you figure out that top triangle and find the hypotenuse from the vertical gauge point, it gives you the diameter of the pin. That is just too easy. The thing that's not easy is you're not going to go to your toolbox or your inspection area and find two identical 0.86.6 diameter pins. So it's nice to know the first method and come up with that little gap correction and go that way. But I had to show you that. Here's your first triangle, same as this triangle right here. Use that as the base leg, use these numbers to have everything fall out, and it gives you the diameter of the ideal pin. Knowing that, you have your gauge block dimension plus one diameter. There's no corrections, there's no secondary triangles to be had. There it is. I will double check this both ways when I do my dovetails, but I had to show you that first. Let's go out, cut some dovetails. Okay, just to prove a point from what I just said on the board. Yep, look at that. Scale slides right under. What does that tell you? That tells you that the depth of the female feature is deeper than the height of the male feature. That's exactly what I intend to do. So if you're going to drive a dovetail, I'm not a big fan of driving it from that corner right there. I would rather drive it from that corner down there, because these two surfaces here and underneath, common of course, are the working surfaces for that dovetail. Driven exclusively by the numbers on the print, you can see how they've got this dovetail dimensioned at the top corner. Well, if this gets deeper and you continue to hit this 500, this bottom closes up. Trust me, it will. So by using the numbers on the print, 500 across the top, 125 triangle right here, do the math, back out the numbers that you need to back out to come up with the across the points in the bottom. Right there. Now once you have across the points in the bottom, you can make this 125 whatever you want. When you do, beware that it's going to get a little thinner on the walls. Make sure you have enough meat to do that. I'm going 5 thousandths deeper on this particular feature than I will on the height of this feature here. And they have 125 and 500, so this thing would be squeaky tight. I'm making mine 130 deep. That's my personal preference. And before I go and I put these actual parts in there, because that's the actual top of the cross slide, and that is the cross slide itself. I'm going to cheat. I'm going to set up. I'm going to use some blanks just to prove the numbers work. No shame in a setup piece, guys. None. Let's do it. First step in the process is to deck the top of this blank off and cut a channel down the center of it to the finished depth of the dovetail. Finished depth is 130. I may go to 129 and clean the bottom up with the dovetail cutter. Check the cutter you're using. Make sure it is a bottom cutting cutter, which most of them I would say are. And let's do this. 355 wide I'm shooting for on this slot. 130 deep. Technically, I just formed the bottom corners of the dovetail. But if you gauge this correctly with the pins, as we're about to do, you can make this wider, and all it will do is result in a break edge on the sharp corners that would normally form. 60-degree dovetail cutter is loaded. And offsetting your features like this 5 thousandths gap that I've put in there, is probably going to help if there's any broken corners on your dovetail cutter. You can also use a 45-degree chamfer tool on the male section to avoid any interference problems in the corners. Going to put a little bit of black Sharpie marker down inside the channel, bring the cutter in and just scuff it, and then we'll work the channel back and forth to achieve the gauge dimension with the pins. At least that's the plan. Let's see what happens. We have a nice crispy dovetail cut in that. I'm going to put the two, I'm using a 126 diameter pin because I had two of those that matched. And that makes the center 166.8. We'll sneak up on that and see if we can get that to work out. I have two different size pins here. One's a 164 and the other is a 167. Knowing that the 164 does not go tells me I have at least 3 more to go. If you want to use an even number, like a 163 pin, that would give you a 4th thou leeway when it doesn't go. So you can make your adjustments, equal distant adjustments, the same amount. So I'm going to take another 2 off of both sides and see what happens. Since the 164 doesn't go, if I add another 4, chances are 168's not going to go. Let's see if that's true. Do it. .164 just sneaks in there. That's beautiful. I like it. All right, looking for 167. If 164 goes, I have another 1.5 thou to go, which means 13.5 each way. Final answer. All went well. That should be a nearly gauge perfect slot right there. 126 pin on each side. You want to mess with a coworker doing this sometime, change out one of the diameters of the pins when he goes to get a cup of coffee. He'd come back and gauge it and watch his color drain from his face. That's just mean, so don't do that. Read about that in the book somewhere. All right, 164 falls in there. 167 should just about stand all by itself. Which it does. I like it. I'm going to leave well enough alone. Set up piece, I'll take it. I got my numbers, I have my cutter. If there are any burrs or anything on this part while it's set up, now would be the time to knock them off. Put another block in there, make the male part. Then we'll put them together. Turns out that cutting and measuring an external dovetail is a whole lot easier than doing the internal. Considerably less math. I'll take you back inside and show you that on the board in a minute. Let's cut this one to 125 tall, and let's go for about 1 thou clearance on the other part I just made. I will use the other part as a gauge. Knowing the diameter of the cutter is important to do something like this because that's what you're working with right now. The radius is from the diameter of the cutter. And for all you guys with really good eyes, yep, I need the deck a little bit more off the top of that part. You're absolutely right. Looking for about 700 over these pins. And if it's anything less, I will be greatly disappointed. But I don't think it will be. Let's see what we got. It's going to be about 20 over. Over. 4.5 more. Both sides. Boy, there's no movement in that. Nice, I like it. There's literally no movement in these blocks. You'd crank this thing back and forth a few times, the aluminum would transfer, it would cold weld, and you'd say, well, okay, I don't know what happened there, but super tight is not always good. But that is exactly what I'm looking for. That is just absolutely beautiful. Nothing moving there. Literally nothing moving. You can see the 5 thou gap between the top of the male part and the bottom one. And just for sake of keeping everybody content, I'm going to take a file and I'm going to break this corner off right here. If there is a radius inside here, it is very possible that they're hitting. So just by knocking that corner off, this fit could get a whole lot easier. See what happens. I'm not getting myself all full of this nastiness. I'm going lengthwise with the edge, so I'm not rolling a burr over either direction. And I'm using a file with no teeth on the edge so I can rest it down on the part itself and not do too much damage. Let's see if that unloosened it a little bit. Oh yeah, it sure did. Look at that. Still an outstanding working fit. Okay, now I have my numbers for both ways. And that little experiment right there tells me that I do have a break edge on this cutter. Not anything too horrible, but it's there. All right, pop it out, get a closer look. Now we got the numbers to do the real part. With minimal deburring off camera, there is the final result. You can see how the 130 on the top piece on the depth doesn't affect anything at all. Fit on these. Just beautiful. Very pleased with that. Let's take a quick trip back to the whiteboard and I will show you the math behind successfully cutting the male. It is so much easier than the female. I'm not even going to touch that line with a 10-foot pole. All right, let's go back on the board for a second. Show you the numbers behind that. Real easy. Let's take a look at the mechanics for an external or a male dovetail feature. This is one side of the plateau. Okay, pin. I used the 126 pin to do the part that I just had. The height does not matter at all if you have this dimension right here. And that is the dimension that we worked from on the female side, because that would be the widest part, or where the pin registered inside. .126 diameter pin against the angle. Where's the math? Because you're going to measure across the outsides of the pins. What do you use? This is really easy. You know that this is the radius of the triangle, right there, the radius of the pin. And just like the construction from before, right angle, bisector. Here's your triangle. 30, 60, 90. 126 diameter. 0.0. You know, I just hate it when the marker makes a mistake like that. 0.063 is the radius, right? The vertical is always half the hypotenuse, so this is 126 as well. And the base, right there. Calculate around here somewhere. Base times 866.03 gives us 109 on the bottom. From here to here, radius from here to here. There is the double dimension. Add them up. 2 times whatever the stack is, plus the required dimension, measurement over the pins. Height doesn't matter. If you're working from the inside corner, it doesn't get much easier than that. Radius gives you the triangle gives you the base leg plus the radius, times 2, added to the dimension you're shooting for, measurement over the pins. There you go. I will apply that to the cross slide and the carriage components in the next video, but I figured it would be a good way to just introduce you to all the triangles and math involved. Try it with a couple different size pins, just work it out. You know, the 30, 60, 90 triangles. This is not going to work for different angles. Things are going to change up a little bit. These 2 numbers will not be applicable. And remember, if you're doing the math and the base leg comes out bigger than the top leg, well, you used the wrong number. Use the other number. The hypotenuse is always the longest leg in the triangle. That's all I got. Thank you very much for watching. Thank you very much for the support. Getting a lot of good messages offline. I very much appreciate that. If I don't respond to all the comments, the volume is a little overwhelming. So I guess that's a good thing as much as it is a bad thing, because I do appreciate all the remarks. Shirts are still available on the website. Check them out. And once again, we're doing good. Stay well. Joe Pye, Advanced Innovations in Austin, Texas. I'm out.